It's a fantastic pleasure to be introducing my PhD grandfather, Professor David Dingley. Many of you have read lots of his papers, I suspect cited many more than you have read perhaps, but they are fantastic to read. I've worked with David for many years now, and so it is a fantastic pleasure to introduce him to give us the invited talk for this afternoon.
Thank you very much. Well, it's very, very pleasant to come here 30 years after the first paper on EBSD was given at an ICOTOM meeting. The title indicates a look back over that 30 years, but when I got the abstracts, and they were very full, and I thought I'd do a word search on EBSD for this meeting, and it came up 258 times. I came to the conclusion that doing a historical survey might not be the most interesting thing to give to such an audience at such a meeting, because obviously EBSD is now second nature, I think, to most of you. So I decided I would go quite quickly into the most recent aspect of EBSD, and that is high-resolution EBSD, a subject at which I'm now still plodding along, trying to provide more information for the crystallographic community, and in this case, the texture community. I stopped my own clock. So I'm going to start, though, with a little bit of reminiscing, if you'll excuse me. So I think it's that one there. And that is the title page of, well, it's the title of that paper given 30 years ago at Los Alamos. It was called electron Kikuchi diffraction then. There was still discussion about what the technique should be called. And below it is a reproduction of some of the pictures that were shown there, the images. The EBSD images we got then weren't that high quality. They were obtained with a SIT camera, which is a very high image gain camera, but there was enough in the image, just about what one needed, to be able to index it online. So it was an online indexing routine. It took about 2 seconds. One had to recognize the zone axes in the figure, just a couple of them, and then the software would do all the indexing. The rather nice image you got there was obtained by using a film camera that went between the specimen and the phosphor screen. And most of the then was done phase identification, as if you know the literature was what we were doing. And the online indexing came a little bit later. But it was by the time that this meeting was held, then the power of the technique began to emerge. There were only a handful of people using it at that time. But the output were the pole figures you're familiar with today. There were, and of course, misorientations between neighboring grains, and also coincident site lattice modeling. That was all built in. And one feature that's in there that hasn't been used very much, and that is the way you represent orientations. And the opening paper of that meeting was by Professor Sir Charles Frank, and he said it's ludicrous that the community uses Euler space to represent orientation. Euler himself, in his second paper, said don't use it. It's a ridiculous way of representing orientation. Use the Rodriguez method. Now, it's now known as the Frank Rodriguez method, but nobody uses it. I'm afraid 30 years later, very, very few. But it was included in this paper, but I just didn't have your room on the slide to show you what it looks like. Nevertheless, what happened at that meeting is Brent Adams, who was at BYU, saw the paper, said, got to go that way because of my interest in texture and modeling of mechanical devices, knowing by predicting the texture they should have. And we set up a collaboration with, I keep hitting the wrong button here. We set up a collaboration, and it was mostly done at Yale University, and later at Brigham Young University, and then finally Brent and I set up the company TSL at Provo, Utah. Now, the main contribution of that collaboration was with his team, David Field, Stuart Wright, Tom Mason, and Carsten Kunze. And that's where the mapping first began. Fortunately, there was another gentleman, Krieger Larsen, working in Denmark, and he provided the Huff transform method of identifying where the Kikuchi bands were in the pattern. And that was then adapted by Carsten into the work done by these collaborators, and out of that came orientation imaging microscopy. And that is not a very good reproduction. If Stuart's in the audience, I apologize for that, but that's, I think, his first mapping of orientations in IOP figures, IPF figures for aluminium. And I think that's the end of the history. So we start on the introduction to the next bit, which is we do texture analysis to characterize the microstructure because we want to know how the material came to be in the state it is when we're examining it, and then what will happen to it when we subsequently put it under mechanical constraint or we thermally treat it. But the deformation inside the sample is just as important as all these other characteristics here. Without knowing the strain distribution or the stress distribution, you're blind as to what's going to happen when you then subsequently put this material under constraint or in a furnace. So the determination of the residual deformation in your sample is as equally important as this. Now, during all of this work, the original work, out came the image quality. And by the way, if Carsten Kunze is in the audience, you took this with me, if you might remember, one afternoon in Utah, BYU, and it's a serial section through a sample, serial done by mechanical polishing, and it's an image quality map. And you look at these features here, a few microns down, you see this grain is now larger, and we're looking at these features which are very clearly, we can see their sub-boundaries, their dislocation clusters showing mechanical damage in the material. And the image quality map is used all the time now to give an idea of what the state of the residual damage and or structural strain in the sample is, but it's qualitative, purely qualitative. But then great contribution from the TSL team, then led with by Stuart Wright, where they said, let's use the orientation measurements we've got within a grain and average it to get some idea what the average misorientation is within a grain, or we could actually look at nearest neighbor misorientations, and it's called a kernel average. And those two there are semi-quantitative. It gives you a bit of a feel for where it's badly damaged or lightly damaged. But one wants quantitative information, and that's this term, high-resolution electron backscattered diffraction. And that's what I'm going to talk about in this talk. So off we go. Just a couple of slides for those that are not familiar with what HR EBSD is about. If we take an undistorted lattice like this two-dimensional representation here and deform it, it skews into this parallelogram shown here. So that the vector R in the original unstrained material becomes the vector R prime in the strained material, and the distortion vector is Q. Now we look on a phosphor screen placed at some distance from the sample, and we see the projection of Q onto the phosphor, so it's lowercase q. And the relationship between lowercase q, and the sample deformation vector Q is this equation here, where lambda is an unknown scalar. This method was published in 2006, just 11 years ago. The paper itself is often referred to as a WMD paper, and the method is known as the Wilkinson Method. Well, this is just the only bit of mathematics I'm going to show today. but it's all described in that paper, the WMD paper. The essential thing is we have to solve this equation. Of course, we can break the deformation on the phosphor screen into an X, Y, and Z component, and those are related to the X, Y, Z coordinates of the vector R that gets distorted, and the distortion in the X, of the X-axis in the X direction, the Y-axis in the X direction, etc. So you end up with these three simultaneous equations. You take pairs of them to eliminate the unknown lambda. You end up with these two simultaneous equations, which have got these 8 unknowns here, and thus we need to make measurements on 7 zone axes in the pattern to be able to establish the deformation tensor in the sample. Right, what we actually measure, and it's important to remember this for something I'm going to say later on, that what we really measure, because we cannot measure out of the plane of the phosphor, we measure this deformation tensor, where the diagonal elements here, the third one out of the paper we get is a 0, we can't measure it, and we get the first and second normal strains are as a difference, A11 minus A33, A22 minus A33. It's important to remember that little thing. Is what I'm going to say later about pseudosymmetry. Now, the viewed surface is in 0 traction, so sigma 33 is 0, and then using the generalized Hooke's law to find out what the strain is with sigma 33 is 0, we put it into here, and we can extract the full deformation tensor from that little bit of geometry on that assumption. And it's a deformation tensor at this stage, and we break it into a symmetric part, which is the elastic strain, and the rotational part, an antisymmetric part, which is the rotation. And that's basically what is done. We have to find a way of doing it, and we do it by a cross-correlation technique. We take a diffraction pattern from an unstrained region in the sample, and we cross-correlate it with the pattern from the test region with which we wish to measure the strength. And we don't measure a single point in the pattern. We have to use statistics, so we draw regions of interest within the pattern, usually 20 to 40, and we take the average displacement of the image within this region of interest with the equivalent area in the reference. And that gives us a distortion average within that area. And we put that distortion average as the center point of the region of interest, and we do that for multiple ROIs. And the reason for doing multiple ROIs is to get some statistics out of this, because measuring any one individual or 4 individuals will give you a scatter. Now, it's very easy to find a reference pattern in a sample such as a single crystal of silicon or germanium. Here we have a nano indentation, and the reference pattern is taken from where this black dot is there. It's that point of the crystal. That's well away from the deformation of the nano indent. And using that, we can be pretty confident that that's at 0 strain. Therefore, the strain and the rotations we measure here, out of that mathematics I just showed you, are absolute. This is an ordinary kernel average map, and in practice what we do is we look for the point in that grain that has got the lowest CAM value. That means to say, surrounding that pixel or that element in the grain, there is very little distortion, because otherwise you'd see it as a rotation. Therefore, using that as a starter, and we do the same in this grain, we can then do the high resolution EBSD work, calculate the strain with that reference, and also we can recalculate the CAM, and we call it a high resolution CAM because our resolution now is of the same order as our strain measurement. That is 1 part in 10,000. We can measure to 1 part in 10,000 rotation between pixels in the sample. And what you see at first is that this CAM value is rather not very accurately representing what's really going on in the material. It's just because that's determined using a Huff transform, which has got its limitations. But here we can see that most of the grain surrounding these indents here, most of it is undeformed. But what's lovely to see is these little marks here and here. That tells us in the CAM, it's only semi-quantitative. It tells us something is going on immediately at the grain boundary, opposite these indentations here. And immediately you can see that there is no corresponding distortion or high CAM value on the opposite side of the grain for an identical indent on this side. So these white marks are indentations around this grain boundary. Okay, now, so we were getting a clue what can be done.